review some of this other stuff. You mean where I left off last time?
Yeah.
Yeah.
Mhm.
Okay, can everyone hear me? Hopefully. I'll take that as yes. Okay, since it's been 5 days or whatever since we went over this, let me just kind of quickly go through what we went over last time. If you've forgotten or were asleep during the last lecture, this is rocks and minerals. And we were kind of just talking about elements, compounds, and mixtures. We did this during another lecture as well. So hopefully this is kind of, you know this pretty well by now. We also talked about this during the periodic table lecture. But yeah, I don't know if you guys were able to review these slides, but if you haven't, I'm just going to go over a few of them before we get on to new material. Let's see where that. So this should all be double review, elements, compounds, mixtures. So chemical formula, we got CO2, basically tells us that there's 2 oxygens and 1 carbon. H2O tells us 2 hydrogens, 1 oxygen. This is basically when we get into more complicated element mixture or chemical formulas, we will be able to know how many of each element or molecule is in this formula. So glucose, for example, what we use, the sugars that we use to get energy is C6H12O6. So that's really confusing if you were to try to draw that out every time. Using chemical formulas is just an easy way to describe what you're working with. So subscript CO2. Subscript is 2. Just tells us 2 oxygen, 1 carbon. Pretty simple. Okay, so we talked most of the time last time about minerals and what is a mineral. This slide is important. It basically tells us all the things needed to have a mineral. It's got to occur naturally. We can't have made it in a lab. It's not living, so it's inorganic. It's solid, so it's not a gas or a liquid. It's got a chemical composition that's definite. So, you have, what do we have? We were talking about last time, pyrite. Fool's gold is P, B, S. So, PBS, pyrite. It looks like gold, but it's not gold. If anyone has hopefully memorized the symbols to the periodic table, Pb is lead, and S is sulfur. So these two things together, you have this yellowy kind of material and this kind of metallic looking thing, and you combine them and they become pyrite, which is fool's gold. And we know because of the chemical formula, there's only one atom that's lead and only one atom that's sulfur. Okay? This is a mineral. This is its definite chemical composition. If you remove the sulfur, it's no longer pyrite. It's just lead. If you remove the lead, then it's just sulfur. It's not pyrite. And it's got a crystal structure. So we talked about this before.
Can you put the mouthpiece a little closer? Can you adjust it? Maybe pull it down or something.
Is that, yeah. I feel like it's pretty good.
Okay. Yeah.
How's that look? Okay, sorry if anyone had trouble hearing me before. Hopefully it's better now. I'll try to speak clearly. So So yeah, this is just the characteristics of a mineral, and it's got to have all of these things. If it doesn't have all of these things, then it's not a mineral. It's just a substance. This is a very specific category that we use in geology. Okay, so we just went over this last time. I'm going to quickly go over this. Non-living, solid. It's got a chemical composition. We just went over that with PBS. Crystal structure. So this is kind of the trickiest part. Basically means when you look at these things under a microscope, or if you kind of look, you can look at them outwardly as well. They have these kind of arranged patterns, and these can be squares, cylinders, blocks, diamonds, anything. But generally, each mineral has a specific way that the atoms are formed in the solid, and that's how you can kind of tell the difference between different minerals. Is they may have different crystal structures. It says here, all minerals have a characteristic crystal structure. And we have about 2,500 minerals in total. These are examples of the structure. You have, the blocky ones up here, the diamond ones up here, and then this thing is just crazy explosion crystal structure. Okay, you can review these if you don't remember from last time. So oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. These are the most abundant elements that make up the Earth's crust. There are 100 that are formed from these. There are 100 minerals that form from these, but they're mostly common, and they're not valuable or anything. They're not like, diamonds or things that are of value, but these are the combinations of these elements form the minerals. Okay, so it's just important to know that you have all of these things kind of coming together in the Earth's crust, and kind of through molten lava interaction, pressure, heat, you can get the formation of these minerals, these crystal structures. And I just kind of went quickly through the other slides, but if you are confused or don't remember from last time, feel free to go back over them. Okay, so this, you don't need to memorize this. We went over this a little bit last time. It's just important to note that there are different types of chemical classifications, and these are basically based on what mineral they form and what elements they're made out of. So this is just a more specific way of describing minerals. Okay, we went through this last time as well. To find out what mineral you're actually working with, say you are hiking around and you find some really shiny looking rock, or a geode, or something that looks like it could be a mineral. How do you find out what that mineral is, or whether or not it's valuable? Could you sell it and buy an iPod? I don't know. You just have to do these tests on it. And the first one is you just want to mainly just look at what it is. What color is it? If it's kind of looks goldish, maybe you have a chunk of gold, but maybe you just have pyrite. And how are you going to know the difference? So this is a chunk of sulfur. It's yellow. Mainly, this is an example of a mineral where you could just look at it and know what it is, or know what it probably is. So color is the first step. Some minerals, though, have different colors, but they're the same mineral. Quartz is a pretty good example. So these are all the same mineral, but they have different colors. So you can't just use color to identify minerals. There's several other ways, most of which are free and easy. So the luster is basically, in very simple terms, how shiny is it? What kind of shininess does it have? We know that diamonds and precious metals like silver and gold, they have this they're shiny, and that's probably why people really like them and find them valuable, is because of this kind of shininess and the fact that they're rare. Um, it doesn't have to be shiny to have luster. Um, we have other terms like glassy, pearly, dull, silky. Um, this just means kind of if you look at something and it doesn't really have, it looks like it's been frozen or something, then it'd be like frosted, or it could be glassy. If it's not shiny when it's exposed to light, might have a non-metallic luster. So this is either how shiny is it or how not shiny is it. This is an example of metallic luster. This is pyrite, like we've been talking about. It's got this blocky crystal structure. It's gold looking, and it's got a metallic luster. So even if you found a chunk of pyrite in a river, and you looked at it and you said, okay, it's gold and it's got a gold luster, like you might think it's gold. You still don't know if it's gold or not. You don't want to just throw it away because it could be worth, 100,000 baht or something. So you want to figure out what this is even more. So you want to test its hardness, and basically you can do this a number of ways. This is kind of a harder test, but this guy, he was a really nerdy German guy. He made this scale of hardness from 1 to 10, and basically most minerals are below 5 or 6, but you have things like diamonds that are around 10. So 1 would be the softest, and 10 would be the hardest. So here it's, talc is like really soft. It turns to powder at any, just to squeeze it hard with your hand and it turns to powder. Diamonds, on the other hand, are almost impossible to cut with normal things. So yeah, Mohs scale, Frederick, the German dude. Streak. So this would be really important if you found a piece of pyrite, because pyrite streaks gray. And it's basically, we went over this a little bit last time. You use, what's going on here? Okay, sorry, this thing is freaking out.
Yeah.
Can you see this? It's like changing slides without me touching anything. I'm trying to go backwards now, but it was.
Let me go upstairs and check. I'll be playing something with the kids.
Okay, hopefully it won't do that again, but this is an example of streak. So this is called a streak plate. You can get it at any local, geology outlet store. Basically, you just rub this rock on this plate, and you get this kind of streak. And sometimes the streak will be much different than what the color of the actual rock is. If you were to take gold and drag it along this plate, the streak would be gold. But if you take something like pyrite, which is lead and sulfur together, you would get a gray streak. So this is kind of, a long, long time ago when people used to deal in gold. This would be a very common test to see, is this really gold, or are you just trying to sell me a piece of pyrite that you found? So this is an example of hematite, which is a common mineral. It looks black when you hold it, but you streak it and it becomes red-brown. So this is another way of identifying mineral. So density. You might remember from some physics lecture that you've had at some point. Density is just the amount of matter in a given space, and it kind of is how much of something is in a specific space. So these atoms that are very close together are going to be that's going to be more dense than a substance where the atoms are further apart. And if something's more dense, typically it's going to be it's going to be the same. It's going to be consistent within a mineral. So we know that a mineral has a definite chemical structure. So using pyrite, which we've been using the whole lecture, you have Pb and S. So it's got this definite structure, and those things, they form this crystal pattern. So if you were to have 100 kilograms of pyrite or 1 gram of pyrite, the density would be the same. They would still have the same structure. The atoms would be the same distance apart. This is not a measure that has to do with mass. This is a measure that has to do with how close are these atoms to one another. So an easy way to think about it is that if you have a gigantic pile of quartz and you have just one rock of quartz, they have equal density. The two materials, because they're the same chemical structure, are going to have the same density. The atoms will be equally placed apart from one another between the two. If you have any questions about density, I encourage you to YouTube density, or you look it up on Wikipedia. There's several really clear definitions. It can kind of be tricky if you just are hearing me say it. But if you look up these videos, I'm sure you can find something. Or feel free to send me an email if this isn't clear. So we went over this as well. What shape is it? Pyrite's got the blocky shape. Diamonds obviously have the kind of pointy shape. These are some words that you don't need to really know, but if you are interested, you have tetragonal, monoclinic, triclinic. These are just describing the shapes of crystals. This is a really fancy diagram just to show you all the different, there's so many different ways that these minerals can have their shapes. This is pyrite right here, and you have PbS. So the red in here is Pb, that's lead, and then you have S, which is sulfur. And when they come together, they form this very organized pattern, and that's the crystal structure. Okay, so cleavage and fracture. This just means if you break the rock, how will it break? Is it going to sheet off in these flat kind of sheets? Is it going to have these bumpy cobbles that are sticking out everywhere? If you've ever seen mica, which is a very common mineral, it's black and it has these sheets, and you can almost peel off each sheet with your hand. And it's very, very characteristic of mica, and if you find something black and it's coming off in these sheets and it's everywhere, it's probably mica. And as this says here, most minerals do not break along smooth lines. So if you were to break a mineral, usually you're going to find that it's going to have a specific way of breaking, and if you can get it to break, obviously, but usually it'll break in maybe its crystal form, or it'll have some weird characteristic. Either way, it gives you some insight as to which mineral it is. So here's a diagram of cleavage, and don't worry about these words. This is just the names of different minerals. This is muscovite, feldspar, halite, calcite, and it just kind of shows you these are how the layers are set up for this mineral. They're set up totally different for this mineral, different for this mineral, different for this mineral. And you know that basically if you break this muscovite, it's going to be coming off to you in layers. This is an example of one layer. And then you have feldspar. If you break it, it's going to have this kind of four-way crisscross kind of break. This thing's got another layer in here. It comes off in cubes. This thing is kind of cubes, but this is more of like a rhombus looking thing than a cube, if you remember, geometry class. But this is just kind of a crooked square. So yeah, you can kind of see that these are all different. These are just other ways of telling what mineral you're dealing with. So special properties, this is kind of just a way of saying everything else that we use to find out what minerals are what. Magnetism. Some minerals are much more magnetic than other minerals. Certain ones glow under fluorescent light. So if you take your, you know, fluorite and you put it under some ultraviolet light, it'll glow a certain color. Some people decide to taste the minerals. Halite tastes salty. I'll take the word for it. I don't really want to taste halite, but if that's your thing. Sulfur smells like rotten eggs. So that yellow rock that we saw at the beginning, if you smell it, it's gonna smell like rotten eggs. If you have some hydrochloric acid and you pour it on calcite, it's gonna fizz. If you just keep hydrochloric acid around the house, but and uranite is radioactive, so you're not gonna really see this too much, but these things are kind of cool. If rotten eggs, things like that. So ores, this is a huge part of minerals and a huge part of actually our culture as humans throughout history. Ores have been kind of sought after for thousands of years. It's basically just a word that describes a combination of minerals that metals and non-metals can be removed from. So an example would be iron ore, copper ore, plutonium ore. It just basically means metals that are trapped in minerals. And when you see a mine, so you have an iron ore mine or a copper mine, then they're going to be mining ores. They're going to be trying to get the metal out of the minerals. And we're going to talk a little bit more about how they do that and why this is useful. If you're listening to your iPod, the headphones that you're using are probably going to have copper wiring in them. We use metals every day for everything, and some metals are extremely valuable, like platinum and things like that. So how do we get the metal out of these minerals? So this is just basically another slide talking about the usefulness of metals. They conduct electricity and heat. If you you cook your food in a metal pot. We went over this in the periodic table lecture. Hopefully you remember it. If you don't, feel free to review this slide. But a metal is just something that it can be a conductor of heat and electricity. It can be pulled into strands, hammered in flat things. It's very malleable. Common examples: iron, lead, aluminum, copper, silver. Really, really important stuff.
Now we need a voice.
And the way to really get this metal out of these minerals is by smelting. And basically, when you heat up a mineral that contains a precious metal, you kind of are able to separate those things enough that you can remove the metal from the ore. So it's just a fancy way of saying heat the thing up until you can get the metal out. Smelting. And maybe if you've seen any pictures of smelting plants, it's just they usually use just really, really hot liquids in order to kind of dump these rocks in there, and then the metal kind of separates out, and they collect all the metal, and then the metal cools down, and they're able to use it to make, iPods and computers and stuff like that. Okay, so non-metals, we kind of went over this as well in the periodic table. They're basically just non-metals. They're poor conductors of electricity and heat. They can't be shaped easily. Sulfur is used at the end of matches because when combined with other things, it becomes very, very good, at igniting. Fertilizers, medicines. These are just basically things that we don't have to put through the smelting process in order to use. So gemstones. Gemstones are interesting because throughout time we've kind of developed kind of a value on gemstones. When you think of a gem, I usually think of, emeralds or diamonds in particular. Um, these are basically rare minerals, and um, they're usually on Mohs scale that we talked about earlier with the hardness. They're usually really hard and very durable. It usually takes a long time for them to be processed um, and created by the earth, and um, they're very, very rare. And you know, basically what happens is they're removed from the earth. Other parts of the mineral that may not be as beautiful are removed in some way. Um, they're cut and polished, and that's what a gem is. So it's important to know that a gem is a mineral, and it just has these different characteristics. Mostly that it's rare and that it's really hard. Um, Diamonds are some of the hardest minerals on Earth. They can only really be cut with lasers. When you have something that needs to be extremely sharp, you can use a diamond if you really want to, if you're really rich. Um, but mostly they're just used as jewelry and things like that. Um, Gemstones, amethysts, zircons, these are known as semi-precious, so they're not going to be, you can buy a rock of amethyst that's for maybe 10 US dollars or 300 baht. You could buy a bunch of amethyst for that. So these aren't what you want. What you want are the diamonds. So if someone's like, I'll trade you some diamonds for your amethyst, definitely do it. These are worth way more, and that's because they're harder and they're rarer, and they're precious stones. Okay, so what is a rock? Sounds like a really straightforward question, but in geologic terms, it's a little bit more complicated. It's just a substance that has more minerals, one or more minerals. So this actually can contain natural substances, organic things. They don't have to have crystal structure. That's the difference. They can just be, combinations of different things that don't form this characteristic pattern. Silica is a big component of a lot of rocks, just kind of hanging out in there. So yeah, this is a pretty good definition. Hard substance composed of one or more minerals. Can also be obtained by naturally occurring substances. So volcanic glass, I don't know if you guys have heard about volcanic glass, but it's really interesting stuff. I don't know if you know how glass is made, but it's generally the heating up of sand or silicates. And when you heat them up and kind of spread them out evenly, they form this glass, which is see-through. We all know glass is windshield. But this is usually by man that this glass is made. Volcanic glass is actually made when a volcano erupts and the lava that spews out the top of the volcano heats up some sort of sand or some sort of silicate and forms glass naturally. So it's not just something that we see in our windows of our cars. There's actually glass in the real world, and it occurs naturally. Glass can also be formed if a lightning bolt strikes a sandy area. You can get glass that way. So pretty cool. This is not the kind of glass you really want to put in your car, but it is glass nonetheless. Okay, so we got three types of rocks: igneous, sedimentary, and metamorphic. It's kind of scary words. Igneous is pretty easy to remember because it's kind of like ignite, like set on fire rocks, and it's basically rocks that were formed originally as magma. And if you guys have learned about plate tectonics or about volcanoes, you know that underneath the surface of the earth is liquid hot magma, and these rocks, as they kind of emerge, magma is pushed to the surface of the earth by one way or another. They form these igneous rocks as they cool. Hey, look at that. Igneous gets their name from the Latin word ignis, which means fire. So just think about fire rock. It's going to be something that comes from magma. So the last lecture we talked a lot about sedimentary rocks. These are basically just rocks that have been weathered and then eroded and then deposited. So this is kind of our last lecture in full right here. And you know, we know that it says, this slide says by wind and water, but we also know this could be by glaciers as well, or by human influence. So these are particles that over time get compacted and squeezed together, or they kind of are fused in some way. They start out as big, you know, and different materials, and they become these rocks, which are just different. They can be composed of one or more minerals. They don't have crystal structure, but they're just kind of all these different sediments maybe, or a specific group of sediments that have been squeezed together into one solid. Yeah, this is just some examples. Detritus is a word here that you probably don't know. Detritus is like living things that are broken down. It's basically like dead life forms of some kind. Detritus. You know, sediments can include shells, bones, leaves, stems, or remains of living things. So when you hear this word detritus, it just means some kind of living thing. Over time, they're pressed together to form rocks. And this can either be by the weight of the rocks above them. It can be by glaciers pushing down on them. It can be by large bodies of water. Anything can kind of compress these 20, 15. Yeah, over time they're pressed together to form rocks. Okay, detrital rocks that form by cementation or compaction are known as detrital or clastic sedimentary rocks. This is basically just a fancy way of saying these rocks that are kind of pressed together. Cementation is just when certain rocks are combined by other substances, kind of forming together, and they kind of make this goo that kind of hardens and becomes this rock, and that's cementation. Subdivided by class, by the size of the particles. So if you have a bunch of small particles together, you can kind of classify this differently as if you have a bunch of large particles that are combined within some sort of cementing substance. So the only way I can really think to describe this in detail is literally, if you have ever seen broken cement, it's a bunch of little rocks kind of with this, they're kind of glued together by this other substance that's a little bit more smaller particles. So yeah, if you don't if you don't understand this, again, please send me an email, or you can look it up on Wikipedia or YouTube. Okay, so this is pretty interesting. Chemical sedimentary rocks are basically rocks that form from a liquid solution generally. So say you have some NaCl, sodium chloride, or salt that's in water, and then over time this water is kind of washing up onto the rock, and eventually the water evaporates from the air, but then the salt is left over. This is called rock salt, and this is a mineral. It's inorganic, naturally occurring, has a crystal structure. It's just once you expose rock salt to water again, it may dissolve again. So these are kind of gypsum is another example of the same thing. Basically, these are rocks that have formed from material that's been in a solution. So they kind of accumulate. You can think about stalactites or stalagmites that you find in caves, those spikes that hang from the ceiling or below that point upwards. Those have been formed because the minerals in the water have been accumulated and they form that pattern, and that is a sedimentary, chemical sedimentary rock. So, just know that these are naturally occurring. They were once in a solution, usually of liquid, and they form these kind of rock structures. Organic sedimentary rock, this is hugely important because, if you know peat or coal, these fossil fuels that we use to power our vehicles or to that used to run, trains and steam engines and everything. This comes from all from animals. So over time, this organic material, the remains of once living organisms, is deposited within the earth. Layers of rock form on top of this, and then this stuff is broken down and becomes this kind of organic rock. And coal is an organic rock formed from plants, and it's a huge source of energy. So when you have coal mines, this is when humans will go deep into layers of the earth, and they'll try to get chunks of coal out and use this coal to do a lot of very, very influential things, whether they're good or bad. Really, this is a huge source of energy, and humans have really used organic sedimentary materials to power their machines for hundreds of years. On a smaller scale, chalk, can come from decomposed sea creatures, and this is what we used to write on an old school blackboard to teach before we had these webcam PowerPoint presentations. I would be using chalk on the board, and that's from decomposed, sea creatures, basically, snails and shrimp and all those things. That's the shell of a shrimp is has calcite in it, and the calcite is kind of pressed together, and that's what we use as a form of calcite is chalk. Okay, so you guys should really be familiar with this word. We discussed it all last lecture. Weathering is just the breakdown from a large rock into smaller rocks. And as you increase the surface area of the one rock by breaking it down, you kind of help it to become eroded or broken down even further into smaller particles. Different things affect weathering. Humans can definitely affect weathering. If certain things are released into the atmosphere, they create acid rain, which can kind of alter the structure of the rock and get it much more prone to erosion, which is called chemical weathering. We went over this mechanical weathering when water gets into cracks between rocks and then freezes. It expands and separates the rock, breaks the rock over time. This can also happen with air in a desert environment when you have air getting into cracks and then expanding. It will push these rocks apart and break them apart. So if you don't remember this from last time, just review this slide. It's pretty helpful in talking about weathering if you either missed the last lecture or are having trouble understanding it. Okay, so an interesting part about some materials is that you have certain minerals are resistant to weathering. So what affects weathering? If you have a really dense material, it's going to be very resistant to weathering. So those precious gemstones that we use, that we talked about earlier, diamonds, rubies, emeralds, They're very resistant to weathering because they're very dense. They're very hard. Quartz is the same way. Um, you often don't find very, very small particles of quartz because it takes much longer to break down. You don't ever really find one little tiny piece of quartz. You usually find it in bigger chunks. So the cement, like the cementation of rocks, sedimentary rocks, is known as lithification. And memorize this if you want to. I prefer if you just understand that certain rocks can be compacted together and they can be glued together by different substances. And it's more important to know what that is than this word. You might hear it enough that you'll eventually remember it, but the process is more important, that these rocks are glued together, compacted together, broken down again, weathered, eroded, deposited, glued back together again, and it's this whole process. And through this process, we get all kinds of different effects on the earth. And hopefully, you can connect this with the last lecture and kind of understand the effects of minerals and the weathering of rocks and lithification. Okay, so cementation. We just went over this a second ago as well, but here's just the bare bones definition. Water-carrying minerals runs over the sediments and deposits minerals that act like glue, sticking them together. So, like I said, if you have a piece of cement and you break it, you'll see little rocks, and they're kind of glued together in this whole kind of situation that looks just like cement, and this happens naturally all over the world. This is another type of kind of rock formation. So we've kind of moved on from weathering, and now we're talking about how rocks are formed. We have the lithification, or the kind of gluing of rocks together, cementation. Compaction is just basically exactly what it sounds like. If you've ever heard of a trash compactor, or if you're unfamiliar with this word, it just means that over time the weight of a certain layer will press down enough onto another layer, and it will create rocks. They could be separate, and then over time they're kind of squeezed together and become one rock. So compaction and cementation are kind of fighting with weathering and erosion all the time. This is just kind of the opposite process of weathering. This is rocks being formed instead of rocks being broken down. And it's important to know that both of these things are happening all the time. And in certain areas, the more compaction is happening. In certain areas, more weathering is happening. And it just depends on the climate that you're dealing with, or whether or not you're talking about in the ocean, underneath the ocean, outside, exposed to acid rain, whatever. These are part of the whole process. Rocks are continually being compacted and continually being weathered. Okay, so back to erosion. Basically, we know that this is the transport of sediment. And you have running water, waves, wind, and really glaciers should be in here because glaciers are huge. We talked a lot about that last time. If you are doubting how awesome glaciers are, I suggest you look it up, because they are amazing forces. And just remember that agents of erosion, running water, huge, waves, pretty good, wind, pretty good, glaciers, just crazy, really, really amazing stuff. Small pieces scary to mention. Okay, so we haven't talked about this, metamorphic rock. So this is basically rock that has been changed a lot, and it's been changed via chemical reactions, because of chemical reactions, heat and pressure. And this is the kind of process that produces precious stones and things that are a little bit rarer. You get this kind of thing going on near volcanoes or areas where liquid hot magma and other things are kind of in contact with the earth, and those things cool down and they heat up, and you get these kind of very special things that happen. So just take away from this chemical reactions, tremendous heat and great pressure exchange existing rocks into new kinds of rocks. So this is just a rock is completely changing based on pressure, heat, and chemical reactions. They're very different from how they start. So, for example, coal, which we talked about before, coal compressed into under thousands of years of heat, pressure, and chemical reaction becomes a diamond. And that's one of the most precious stones we know of is a diamond. And it started out as a piece of coal, which is very common. It's a metamorphic rock. It becomes a mineral. So that's pretty interesting. So where am I going with this? Where have we been discussing all these processes for? You could look at this in the big view by the rock cycle, and this is basically how rocks change, and over thousands of years, one rock might become another rock, get broken down, get deposited, get compacted, be exposed to heat, all these pressures, and then it could become the original rock that it was when it started. So this is basically talking about long periods of time. There's no definite sequence because, say, you have a volcano, you're not necessarily going to have a volcano every year. That's going to affect all the rocks. You have an earthquake, that's going to affect the rocks. It's got no definite sequence. It's got no pattern. But we do know that rocks are continually being weathered. They're continually being eroded. They're deposited. They're compacted. They're metamorphosized. They are exposed to all these different forces, and if you look at them from a long period of time, you have the rock cycle. I'm going to end there because this is very important, and I'd really like you to take this away from what we talked about today. It's, basically, it's circular. You can't have things breaking down all the time. If things were just breaking down, then you would have just sand everywhere. Instead, what you have is things breaking down, things moving, and things being pushed together again. So just as much as one mountain may be becoming nothing, another mountain might be forming at the same time. And if you look through millions of years, you can see through different techniques used by geologists that this has been happening since Earth began, and it will continue happening. Hope that was not too confusing. Again, if you are confused, you can access the slides on the website or send me an email. Thanks a lot. Bye.
Okay,